In this lecture, we are going to formulate the main equation, which is the purpose. Solving that equation is the purpose of any solid or continuum mechanics problem. And this equation is the equilibrium equation. So we're not going to cover the mass balance equations in this course, in this undergraduate course, but what we're going to cover is the differential equation of equilibrium, which any problem in solid mechanics attempts to solve. So basically, any problem in continuum mechanics or solid mechanics is interested in the following. Given an object in space with certain boundary conditions and certain forces applied to that object, what is the deformation shape of this object? What is the new position function x as a function of the old coordinate? What is that function? And to find x, we need to solve a differential equation, and this differential equation is the differential equation of equilibrium, which is based on Newton's equation. So what we're interested in, what is the deformation, and what is the stress and strain distribution on the object. And in order to formulate the equation, we need first to assume something about the variables that we're trying to solve for. So the variables that we're trying to solve for are usually the stresses in the object. So we know that the stress has 6 components, 6 independent components. Given a certain coordinate system, and it's symmetric, and we assume that all the components are continuous and smooth. The components of the stress matrix are continuous and smooth. What does this mean? It means if I take any cross section, let's say any cross section along x, let's say x is the first component or the horizontal component in the direction of E1, and I plot the value of sigma on 1, I will get a smooth curve. And because this is a smooth curve, I'm able to do the following. Let's say this is value x, and this is x plus a little bit more, delta x, and this is sigma on 1 at the distance x. At the distance x plus dx, because sigma on 1 is continuous and smooth, I'm able to assume that sigma on 1 at x plus delta x, I can use a Taylor approximation, which is basically assuming that this value is equal to sigma on 1 at x plus a little bit more. This little bit more is related to the first derivative of sigma on 1 with respect to x multiplied by delta x plus some other terms that I can later ignore. And because I'm able to assume the continuity of those variables, I'm able to form differential equations. So let's apply this on a continuum. Let's use this Taylor approximation in a continuum to try and find the forces acting on a small element of the continuum. So given a continuum where there are external forces acting on the continuum, and let's say I have a gravity field. The gravity field is acting in this direction, for example, which means it has 3 different components. So assume gravity field in a general direction. So assume that the gravity field has an acceleration g, or I'm going to call it b, where b is a vector made out of b1, b2, and b3 because it's acting in a general direction. So this is the gravity field vector b, or g. You're used to the symbol g, but in continuum mechanics the symbol b is used instead, which has the 3 components b1, b2, and b3. And inside this continuum object, I'm going to extract a small cube with dimensions delta x capital 1, or I'm actually going to extract those this object from the deformed configuration. So assume this is the deformed configuration. I'm going to extract a small cube with the dimensions dx1, dx2, dx3, and I'm going to look at that object, or that box. The horizontal is dx1, the vertical is dx2, the third direction is dx3, the forces acting per unit volume, the gravity forces acting per unit volume are rho b1, rho b2, and rho b3. The stresses on the forces behind, on the faces behind, are sigma 1 3, sigma 3 2, sigma 3 1, sigma 3 3, sigma 3 2, sigma 2 1, sigma 2 2, sigma 2 3, sigma 1 1, sigma 1 2, sigma 1 3. These are the stresses acting on the faces that are behind the box. On the faces that I'm looking at here, if this is sigma on 1, then the value of the stress here is sigma on 1 plus a little bit more, due to assuming that sigma on 1 is a continuous and smooth function. So I can use a Taylor expansion and say that between the back face to the front face, sigma on 1 has changed with a little bit that is related to the partial derivative of sigma on 1. If this is sigma on 3, then right here I have sigma on 3 plus a little bit more. If this is sigma on 2, I have here sigma on 2 plus a little bit more, and so on. So all those stresses that are in the back faces, in the front faces, they have increased by a little bit more. So in the back here, for example, I have sigma 3 3. In the front face here, I have sigma 3 3 plus a little bit more, which is how much sigma 3 3 changes with respect to x3 multiplied by the change delta x3. after doing this, I'm going to write the Newton's equations of equilibrium, which state that the sum of forces are equal to the mass multiplied by the acceleration. Now I'm going to do this 3 times. The sum of forces in the direction 1 are equal to the mass multiplied by the acceleration in the direction 1. The sum of forces in the direction 2 are equal to the same mass multiplied by the acceleration in the direction 2, and the sum of forces in the direction 3 are equal to the mass multiplied by the acceleration in the direction 3. So the first equation all the forces in the horizontal direction. The first force is sigma on 1 multiplied by the area, and the area is dx3 dx2 plus, so let's know this will be negative because this is positive, this direction is positive, and the opposite direction is negative. So I have sigma on 1. I also have sigma to 1, also in the negative direction, so minus sigma to 1 multiplied by the area, and the area of the bottom face here is equal to dx1 dx3. I also have sigma 3,1, so minus sigma 3,1 multiplied by the area, and the area of the back face is equal to dx1 multiplied by dx2. So these are all the horizontal forces acting on the back faces. On the front faces, I have in the positive direction sigma on 1 plus partial sigma on 1 by partial x1 dx1. This is the stress multiplied by the area, and the area is dx3 multiplied by dx2. Plus this guy, which is in the horizontal direction, plus this guy, which is in the horizontal direction. So I'm going to write both. So plus sigma to 1 plus partial sigma to 1 by partial x2 dx2 multiplied by the top area, or the area of the top face, which is dx1 dx3, plus sigma 3,1 plus partial sigma 3,1 by partial x3 dx3 multiplied by the area of the front face. The area of the front face is dx1 multiplied by dx2 plus the mass multiplied by the horizontal component of the gravity vector. This is equal to mass multiplied by the acceleration. Now the mass of this object is equal to its density multiplied by its volume, which is equal to rho multiplied by dx1 dx2 dx3. So I'm going to substitute rho multiplied by dx1 dx2 dx3 for the mass, and then I'm going to divide by the volume. But before I do this, notice that negative sigma on 1 dx2 dx3 cancels sigma on 1 dx3 dx2. Negative sigma to 1 cancels sigma to 1. 3,1 cancels 3,1. And I'm left with the following components. Partial sigma on 1 by partial x1 dx1 dx2 dx3 plus partial sigma 2 1 by partial x2 dx1 dx2 dx3 plus partial sigma 3 1 by partial x3 dx1 dx2 dx3 plus rho dx1 dx2 dx3 b1 is equal to rho dx1 dx2 dx3 multiplied by acceleration 1. And then I'm going to cancel the volume, and I end up with the first equation of equilibrium that states partial sigma 1 1 by partial x1 plus partial sigma 2 1 by partial x2 plus partial sigma 3 1 by partial x3 plus rho b1 is equal to rho a1. Similarly, if you follow the same procedure to write the equation, the sum of forces equal to the mass multiplied by the acceleration in the second direction, you will get the following equation. And the same, when you sum the forces in the third direction, you will get this third equation. So, right in front of you, you have three equations of equilibrium. Those three equations are what we need to solve to find the acceleration and the stresses inside the continuum using different boundary conditions. Now, these equations can be written in a simpler form by simply saying sum from j equal 1 to 3 partial sigma ji by partial xj plus rho bi equal rho ai, where I is equal to 1, 2, or 3. So you have three equations, and those three equations can be written in this much simpler form. The sum of parts, so put j is equal to 1 and I equal to 1. So when when I is equal to 1 and j is summed from 1 to 3, you get the first equation. Partial sigma 1 1 by partial x1, partial sigma 2 1 x2, 3 1 x3, plus rho b1 equal rho a1. If you put I equal 2 and repeat, you get the second equation. If we put I equal 3 and repeat, you get the third equation. So what we're trying to do is solve the equations of equilibrium. So the definition of a continuum mechanics problem is as follows. Given an object described by a set of vectors omega naught and boundary conditions of displacements u equals 0 or u specified, and boundary conditions of stress or forces per unit area or traction vectors. I know sigma transpose n on the surface. I know Tn, which is equal to sigma transpose n equal given on part of the boundary. And the displacement is specified on part of the boundary. I'm going to call this part gamma or omega u. I'm going to call this part omega n. And what are the stresses that satisfy the above boundary conditions? And the equilibrium equations at every point. And the equilibrium equations are given as the sum of j equal 1 to 3 partial sigma ji by partial xj plus rho bi equal rho ai, where I equal to 1, 2, 3. For a static problem, rho ai is equal to 0, and the equation of equilibrium boils down to finding the stresses that satisfy partial sigma ji by partial xg plus rho bi equal to 0. Now, solving these differential equations is not an easy task, and we require, in most cases, we require finite element analysis to be able to solve these differential equations of equilibrium. So we require a numerical method to solve those differential equations of equilibrium. And the reason why they're not easy, because of we have two difficulties that I'm going to discuss right now. So difficulties associated with the above three equations. One, the boundary conditions are given in terms of the displacement. Some of the boundary conditions, some boundary conditions are given in terms of u, but u does not appear in the equations itself. And the other difficulty is we have three equations, yet the unknowns are, so we have three equations to find 6 unknown stresses or stress components. So we have more stress components than the actual equations that we're trying to solve, because the unknowns are sigma on 1, sigma 2 2, sigma 2 3, or sigma 3 3, sigma 1 2, sigma 1 3, and sigma 2 3, And you should recall that we already used the sum of moments equal to 0 to prove that sigma 1, 2 has to be equal to sigma 2, 1, sigma 1, 3 has to be equal to sigma 3, 1, sigma 2, 3 has to be equal to sigma 3, 2. So we already used the equations of moment equilibrium to prove that the stress matrix is symmetric, and so we still have 6 unknowns to find, and these 6 unknowns we only have 3 equations. To overcome those difficulties, we still need to introduce in the next chapter we will use the constitutive laws to replace the unknown stresses with 6 strains, which are functions in 3 variables, u1, which are the displacements. And so we can, in the next chapter, we'll see how we can replace the stresses with the strains. But for now, we're going to utilize, we're going to present 2 problems, or no, for the remaining part of this chapter, we're going to show 3 problems showing how we can use, or how we can solve the differential equation of equilibrium, or how we can use the differential equation of equilibrium. And usually, in order to solve the differential equation of equilibrium in its current form, we have to introduce very severe assumptions or very severe restrictions to be able to reduce the number of unknowns and to be able to solve and find some of the stress components. In the first problem, it's just a direct application of the equations of equilibrium. I have an object, and I know that this object is in static equilibrium, and this object is embedded in R3. And the stress at every point inside the object is given by this matrix. Sigma 1 is equal to this, sigma 1, 2 is equal to this, sigma 2, 1 is equal to this, and so on. So we have the 6 components of the stresses. Now for this stress to be in equilibrium, there has to be some sort of gravity field that is pulling this object, that's causing it to have this stress matrix. And the objective of the problem is, what is this G, or what we call B. And B has 3 components, B1, B2, and B3. What are those components? So what do we know? We know that we have 3 equations: partial sigma ji by partial xj, the sum from j equal 1 to 3, plus rho bi, static equilibrium, equal to 0. So rho b1 is equal to partial sigma 1, 1 by partial x1 plus partial, negative, all this is negative, partial sigma 2, 1 by partial x2 plus partial sigma 3, 1 by partial x3. Partial sigma 1 by partial x1 will be equal to 10x1. Partial sigma 2, 1 by partial x2 is equal to negative x2. Partial sigma 3, 1 by partial x3 is 0. So this is equal to negative 10x1 plus x2. I'm sorry, this is x1. Partial sigma 2 1 by partial x2. So sigma 2 1 is equal to negative x2 x1. And partial sigma 2 1 by partial x2 is equal to negative x1. So this is equal to negative 9x1. And similarly, rho b2 is equal to negative partial sigma 1 2 by partial x1 plus partial sigma 2 2 by partial x2 plus partial sigma 3 2 by partial x3. This is equal to negative partial sigma 1 2 by partial x1 will be equal to negative x2. Partial sigma 2 2 by partial x2 is 5 plus 0. So this is equal to x2 minus 5. And if you continue this, rho b3 will be equal to negative 18 x3. And so the gravity field, or what we call the body force field, or in other word, the gravity field, is equal to rho b1, rho b2, rho b3, which is equal to negative 9x1, x2 minus 5, negative 18x3. In the next problem, we have a vertical beam with a varying circular cross-sectional area. At the bottom, the radius is equal to 2 meters, and the top r is equal to 2 meters, and at the bottom r is equal to 1 meters. And the radius varies linearly. Linearly means this is E2. If this is x2, then we can find r at a distance x2. R at a distance x2 is equal to 2 minus this, which will be equal to x2 over L. When x2 is equal to L, r is equal to 1 meter. When x2 is 0, r is equal to 2 meters. When x2 is any other intermediate value, r is equal to 2 minus x2 over L. This beam is used to carry a concentrated load of P equal 50 Newton and has a density rho that's equal to 20 kilogram per meter cubed. And is subjected to a gravity field with G is equal to 10 meter per second squared. So I have P in the direction 2 is equal to G is equal to 10 meter per second squared. in order to be able to solve the differential equation, I have to make restrictive assumptions. And the restrictive assumption that I put here is that the only non-zero stress component is sigma 2, 2. So basically, I'm assuming that the stress matrix that has so many components I'm assuming that all of them are 0 except sigma 2, 2, which is a really huge restriction, but that's the only way I'm able to solve such a problem, even with such a simple geometry. The only way to solve this problem is to assume such a restrictive assumption. So I can start from the differential equations that I have given you, but I'm going to start again and extract a small sliver of that material or that beam and try to see what forces are acting on that sliver. So when I extract that sliver, I know the following. That this is the direction of increasing x2. That if the stress here is sigma 2, 2, then the stress here has to be equal to sigma 2, 2 plus a little bit more. The reason why I'm able to write this little bit more is because I'm assuming everything is continuous and I can use a Taylor expansion. And if this top part has an area A, then the bottom part has an area A plus a little bit more. What are the other forces that are acting? The other force that's acting is the body force or the gravity field, which is acting rho multiplied, basically mass multiplied by g. The mass is equal to rho multiplied by the area multiplied by dx2 multiplied by g. These are all the forces that are acting on my object. Before we continue, I already have an expression for A. What I'm looking for is what is sigma 2, 2. Before I solve for sigma 2, 2, I'm just going to write the expression for A. A is equal to pi r squared, and r is equal to 2 minus x2 over L squared. And partial A by partial x2, because I need it in this equation, is I can calculate it. But I'm just going to leave it partial A by partial x2 because it will be easier for me when I write the equation. So the equation of equilibrium is the sum of forces in the two second direction is equal to 0. Why 0? Because I'm assuming static equilibrium. Ma2 equal to 0. So the top force is negative sigma 2, 2 multiplied by area. The bottom force is the stress multiplied by the area. What is the area? It's A plus partial A by partial x2. So the top force, the bottom force, plus the gravity field all this is equal to 0. So let's write this equation: minus sigma 2 2a plus sigma 2 to A plus sigma 2 to partial A by partial x2 dx2 plus partial sigma 2 2 by partial x2 dx2 A plus partial sigma 2 2 by partial x2 partial A by partial x2 multiplied by dx2 multiplied by dx2 plus rho A dx2 g. This is equal to 0, and then if I divide by 1 dx2, so this will cancel this, and then 1 dx2 will cancel 1 dx2 will cancel 1 dx2 will cancel 1 dx2. After this dx2 is gone, you're going to find that this expression still has a dx2, which means it still can, this expression can be neglected. And I'm going to be left with the following equation: sigma 2 2 multiplied by partial A by partial x2 plus partial sigma 2 2 by partial x2 A plus rho A multiplied by g is equal to 0. So this is my differential equation of equilibrium, and I'm looking for what is sigma 2 2 that satisfy this differential equation, where I have the area as a function of x, and I have partial A by partial x2 also as a function of x, which is equal to 2 pi 2 minus x2 over L multiplied by negative 1 over L. So I have this value, I have this A, I have G given, and I have rho given. So I have all the numbers. All I'm looking for is what is the function sigma 2 2 that can satisfy this equation, and I'm looking for some boundary conditions. What are the boundary conditions? The boundary conditions are, if you look at your problem, right here, we know the stress. The stress is given by 50 divided by the area. So at x2 equal to L, sigma 2 2 is given as the force divided by the area. The force is 50. And the area is pi r squared, which is 50 divided by pi, and r is equal to 1. So given this boundary condition, sigma 2 2 at x2 equal L, and given this differential equation, what is sigma 2 2? Now, this is a really complicated equation. I don't want you to know how to solve it by hand. You can just simply use Mathematica, and I'm going to show you in a different tutorial how to solve this equation, or you can check the Mathematica code in your textbook. And the solution is in fact equal to 1 over 3 multiplied by 2000 minus 23806.3 divided by x2 minus 10 squared minus 200 x2. So you can see it's really not a simple, even though we've made so many restrictive assumptions, we've assumed that all the other stress components are 0, and we've done all sorts of different assumptions, and yet the sigma 2 2 is still a complicated problem, and that's why in most cases we use finite element analysis, which is a numerical technique and utilizes sophisticated computer programs to solve for all the different stress components within a continuum. The last problem in this section is a similar problem. but perhaps the solution will be much easier because the geometry is slightly more, it's easier. I have a horizontal beam given density and given a constant body force or a constant gravity vector of B1 that's equal to 10 Newton per kilogram in the direction of E1, and notice that that B1, which is equal to 10 Newton per kilogram, is basically 10 kilogram meter per second squared per kilogram, which is equal to what you're used to, the gravity field G given in the acceleration vector. Again, we have to assume restrictive assumptions to be able to solve for the stress fields, and the restrictive assumption is that the only non-zero stress component is sigma on 1. We need the distribution of sigma on 1 along the beam. This is very similar to the previous problem, but the boundary condition of the stress on this edge is given as 20 Newton per meter squared. And so I'm going to extract this sliver from the material with a width of dx1. This is sigma on 1. This is partial sigma on 1, or this is the same sigma on 1 plus a little bit more. This little bit more has to do with the partial derivative of sigma on 1 with respect to x1 multiplied by dx1 plus other terms that I will ignore. And I have another force that's equal to B1 multiplied by the mass, and this is the area, and this is the area, and the area is constant. So again, the sum of forces are equal to 0. Sigma on 1a plus sigma on 1 plus partial sigma on 1 partial x1 dx1 multiplied by the area plus rho multiplied by the mass, which is area, rho multiplied by the volume, which is area multiplied by dx1 multiplied by rho, equal to 0. Sigma on 1 will cancel, and you're going to be left with partial sigma on 1 by partial x1 dx1 will cancel dx1. In fact, the area will also cancel the area, and you'll be left with partial sigma on 1 by partial x1 plus rho b1 equal to 0. So partial sigma on 1 by partial x1 equal to negative 10 multiplied by rho, and rho is given as 1. So sigma on 1 is equal to negative 10 x1 plus a constant, and boundary condition is given as 20 when x1 is equal to L, at x1 equal to L, sigma on 1 is equal to 20, which means 20 equal to negative 10L plus C. That means C is equal to 20 plus 10L. Therefore, sigma on 1 is equal to negative 10 x1 plus 20 plus 10L. So this concludes this chapter of the differential equation of equilibrium. In the next chapter, we're going to study the constitutive laws. Constitutive laws allow us to replace the stresses that appear in the differential equation of equilibrium with the strains, and the strains are functions of the displacements, and thus the three equations of equilibrium that we have, sum of forces in the x direction, sum of forces in the y, sum of forces in the z, they become functions of the displacement vectors, which make the equations allow us to solve the equations. And of course, to solve the equations, we finally need to use a numerical method, and this is what we're going to cover at the end of this course. We're going to start covering numerical methods to solve the differential equation of equilibrium.